Okay, let's continue. So everything we did so far is in 1D, but our problem is not, like our universe is not one-dimensional, right? So it's boring. So now we move to higher dimensions. The nice thing is that when we move to elastodynamics in higher dimensions, everything that we saw for 1D is going to translate nicely into 3D. That is why we start with 1D, because, well, things are easier to understand in one dimension, but they translate nicely into higher dimensions. So obviously the first thing we do again, we're going to have to try to set up the strong form of our initial value problem. And so we start by looking at a very, very small piece of our domain, and then let's see what are the forces that are lying on it, okay? So if I take, this is my now mechanics potato, as you will probably have seen thousands already in your studies. This is one nice one, created by Tix, by those of you who love LaTeX. We have our traction boundary condition here, gamma n. You have our Dirichlet boundary condition here, right? And then, well, and what is a point here, lying on the boundary that doesn't have a traction? What is that, Dirichlet or Newman? Newman, right? It's just it has zero traction, but still Newman. And so we grab a small piece of infinitesimal potato, right? And let's see what are the forces that are acting on it. So these are our little cube. And again, I'm going to be looking at forces that are acting only in the x direction. So you know the stress tensor now has how many components? 9 components, right? And so if I take only the components that are going to lead to forces in the x direction, you have obviously the sigma xx that is acting perpendicularly to basically that plane dy dz, right? Then I have, this is of course the let's say the normal component of the stress tensor. Then you have the shear components. This is my sigma xy. That is of course acting on this face here, is dx dz. Here you have the axis for that infinitesimal cube, and then you have this one here, right? Basically acting perpendicularly to the plane dx dy. And so of course we have 2 of those forces. Here you have the one on top, but the one in the bottom element is looking like that, pointing in the other direction. So in addition to all the forces that are created by the stresses, of course you have the effect of the inertial effect, right? So you have now density, so it's basically mass per unit volume, and so we're going to have to multiply that by the volume dx dy dz of this infinitesimal cube. And you also have well, this, let's say, body force, if you want, bx. In essence, I use the same symbol as body force because normally we're dealing with gravity loads, for instance, right, in 3D. And since I wanted to have something similar in 1D, of course, we kept that in the one-dimensional with the same symbol so that you see that it is a nicer way to transition to higher dimensions. Okay, when we write second law of Newton, then with all these forces, you get, of course, the effect of all those stresses acting on those faces. And then we have basically the effect of the body force right there. And then finally, on the right-hand side, you have mass times acceleration. So you have the density, you multiply that by the volume, then you have the actual mass, and then the acceleration in the x direction, right? And so if I now take this equation and I divide by the volume, right, dx dy dz, and, well, I do that and I apply the limit as my infinitesimal volume goes to 0, then I get my differential equation in the x direction, right? Very straightforward to get the dynamical equilibrium equation in 3D. Very, very simple. It's actually the same thing as in 1D, but we obtain one equation. So how many equations we have? 3. So now we have 3 equations, okay? So we do the same in 3 with the other 2 directions, and then we get into this equation where we have the divergence of the stress tensor, right, plus the body force minus rho times the acceleration is equal to 0. So now we have 3 equations. That's why it's equal to 0 vector. So that 0 vector has 3 components. So because this is actually 3 equations, right? And that has to be the case. So this has to hold for all x and t. Notice that now x is a vector, right? It's no longer a scalar, as it was in 1D. In omega cross 0t, we're still interested in finding out the solution in that time interval, right? Very, very straightforward. It's exactly the same thing. Here I wrote, well, this denotes the divergence operator, and then you have Cauchy stress tensor, right, which is indeed a tensor, and then B is a vector, and so finally my density is a scalar, okay, density. Okay, that's it, that's the equation. Do we like that? What are we missing to get the strong form? Boundary conditions, initial conditions, and so everything remains the same as in the one-dimensional case, right? So we supplement our dynamic equilibrium equation with initial conditions. So now we know the state of our potato at time equal to 0. Those are my initial conditions. And then my boundary conditions, notice that I have u is equal to u bar. I'm prescribing the displacement again at some part of the boundary. And now I prescribe the traction. So this is the so-called, do you know how this equation is called? That is relating the stress to the tractions at the boundary. Cauchy, thank you so much. Yeah, that is Cauchy traction formula. That is the one that relates the stress to the boundary tractions. Very nice. So now we have the complete statement, right? Of course, we are assuming that there is still linear behavior between stresses and strains. This is Hooke's law, where this C now, since now the stress and strain in higher dimensions is a second order rank tensor, right? So now the let's call it the tensor C is a fourth order tensor. So what is a fourth order tensor? Well, what is a second order tensor? Who can tell me? No, it's not a matrix. A tensor is not a matrix. The fact that you can express a tensor like a matrix is something different. In that way, they are similar, but as a tensor is not a matrix.
It's a function from vector to vector.
It's an object that operates on a vector to create another vector. Pretty much what you said. That is the mapping that you are discussing. It's an object that operates on a vector to create another vector. All right, so what is a fourth order tensor? If a second order tensor is an object that operates on a vector to create another vector, a fourth order tensor is an object that operates on a second order tensor to create a second order tensor. Right? That is what this C is. And we're going to talk about C because we don't like fourth order tensors when we do computation. Because imagine, if I can represent a second order tensor like a matrix, do we like matrix when we do computation? Oh, we love matrix. Everything we do is matrix based, right? But it's because we can nicely arrange elements in a matrix, we can index nicely, and we can slice nicely, right? But imagine a fourth order object, right? How many indices we need? 4. Yeah, can we create 4-dimensional matrices? Yes, we can, but they are a pain in the neck to work with, right? So we don't like slicing four-dimensional. So we're gonna talk about the trick that we play in finite element modeling so that we can lower the dimensionality of those tensors, right? Okay, finally, here we have strain. Notice that I'm using the linearized strain tensor. So everything we do is linearized kinematics. So everything that we're going to be discussing here is not large deformation, finite deformation kinematics. It's small deformation kinematics. In other words, this is not the complete strain tensor. It's the linearized strain tensor. What does that mean? Who can tell me?
That you're not capable of expressing rotations very well.
Sorry?
That you're not capable of expressing rotations very well.
Yeah, that is actually a good point. What happens when you try to rotate something with small deformation kinematics? Have you ever tried this? Have you ever tried to rotate a rigid body rotation into a finite element mesh that is just using small deformation kinematics? Have you tried this?
No.
What happens?
You get a strain.
Huh?
You get a non-zero strain.
You don't only get normal strain. What do you see? What is the result? What do you see? It's just a rigid body rotation. What do you see?
I mean, it constrains the whole thing, but
your mesh blows up. Your elements increase in size. It's horrible. So, indeed, rotations are not nicely expressed when you use small deformation kinematics. Yeah? So that basically means, is this completely useless? Well, not really. I mean, if you don't see really finite deformation in your simulation, and you're not going to be dealing with rotations, you can still get really accurate results. So let's move on, because there is really a nice, we can get to a really nice formulation in the end, all right? Okay, all right, so as we discussed multiple times already, we don't like the strong form, especially in higher dimensions. Getting to the exact solution of a strong form is impossible. Particularly in dynamics. Remember that this equation has to hold for every single point in our mechanics potato and at every single point on time. And on top of that, you have to satisfy boundary conditions. That's not possible. Like, forget about it. No way. So how do?
Weak form.
We try to satisfy that on average. So we grab our differential equation, right? And we say, well, I'm going to multiply that by a test function or weight function. Notice that now we are dealing with vectors. So now we are going to be working with vector-valued function spaces. What does that mean? Well, if you take a vector, every component of that vector is going to be a function. That is a vector-valued function spaces, right? So if I now set my orthogonality condition, I say, well, this is my differential equation. I'm going to do the dot product with that vector-valued test function, and I'm going to set that equal to 0. Notice that 0 is not a vector anymore, it's a scalar. Why is that? Well, because it's a dot product between two vectors, that's actually a scalar. So that is going to be equal to 0. On average, this is going to hold for all vector value test functions in some conveniently chosen space. Again, we talk about the same thing we talked for the one-dimensional case. We're dealing with smooth functions, kinematically admissible. In the end, we're dealing with what spaces? Sobolev spaces. Remember? We use Sobolev spaces. Now, it turns out that every component of our vector has to belong to the Sobolev space. That's all it means. All right? Yeah. And okay, well, I wrote it here at the bottom as a footnote. So the vector spaces we're going to be dealing with are vectors V. In RD, that basically says it's a vector for every point in my domain, such that each component, and I say each component VI, and I goes to 1 to 3, remember we're in 3D, right? Each component is a function that belongs to H1. H1 is our first order Sobolev space, right? So very fancy mathematical way to say that, well, now I'm going to be using vectors, and each component of that vector is going to be a function that I can integrate, and the result of that integral has to be finite, and the result of the derivative of that function has to be finite. Right? It's in H1. Okay? All right. When we do that, let's try to work a little bit on that expression. So we're going to use this identity, and I could prove it to you that this is actually true. For now, trust me, I'm going to give you a reference if you really want to check. Let's see if Alejandro, is it true what he said? Well, this is the case. So what we have here is essentially the dot product between W and the divergence of a stress tensor. So remember, the stress tensor is a second order tensor. So when we apply the divergence to a second order tensor, we get a vector. So this whole thing is a vector. When I apply the dot product with a vector, we get a scalar. So this whole thing on the left is a scalar, right? Then that is equal to, if I apply this here, we have a second order tensor operating on a vector, I get a vector. If I apply the divergence on a vector, I get a scalar. So this whole thing is a scalar. So dimensionally, we are good so far, right? And then the final term here, we have the so-called contraction. So if I apply the gradient to a vector, I get a second order tensor. So this whole thing here is a second order tensor. And sigma is a second order tensor. So how do I get the scalar out of that? Well, I apply the so-called contraction operation. So basically, I go to the 1,1 component of the first tensor, and I multiply by the 1,1 component of the second tensor, and then plus the 1,2 component of the first tensor, multiply by the 1,2 component of the second tensor, plus, and I keep going like this. It's like, think about it as a dot product between two matrices. Again, tensors. I don't want to say matrices, not the same thing. Okay? All right, so this whole thing here is a tensor. Now, of course, you can write this component-wise, and you very easily check that this identity holds. This is something that I have in my book. There is a proof at the end. I will give you a link to the book at the end because it just happens to be free for all of you, and it's a nice read in case you don't have anything to do a Saturday afternoon, right? Anyways, yeah?
You're the author of the book, right?
Yeah, I'm the author of the book. Yeah.
That was the question.
Yeah. I'm the author of the book. Anyways, let's move on. So now that we have this identity, we can apply it here, and then you see nicely, right, that we have that guy where we have basically the contraction between two tensors. This is the result of this identity. And then on the right-hand side, we have this we didn't modify, we didn't touch, the same as the inertial terms. It was not even, we didn't touch it, right? It was just like that. But because of this identity, we have this term and that term here. And this right-hand side here term is very, very interesting. Notice that even though we all know that the stress tensor is symmetric, right? We know that is the result of the balance of angular momentum. We know that the stress tensor is symmetric. I have not used that property. So I could have basically chosen to put sigma there, but I put sigma transpose because I don't need to use the property of the symmetry of the stress tensor. And I'll show you why in a minute. Right? So let's look a little bit at that object. Now we are going to use something called the divergence theorem. I'm going to convert this term here, that is basically the divergence of this whatever quantities inside that, right? I can apply the divergence theorem and transform that integral over the entire body of our mechanics potato into an integral that is only acting on the boundary. So that is what the divergence theorem allows you to do, right? It's like Gauss theorem. It's like integration by parts of higher dimensions. So that is essentially the subtlety I mentioned in the beginning, right? The 1D translates, or we can transition nicely to higher dimensions, except for a couple of subtleties here and there. So integration by parts, now we use Gauss theorem or the divergence theorem, right? So what is the divergence theorem? Well, we take that guy and we say, well, I'm going to just, this is going to be equal to an integral over my boundary, and I take this thing here that is inside the divergence, right? And I'm just going to operate it by the, do the dot product with the normal. And that's all there is to it. All there is to it is simply taking this guy, do the dot product with the normal, and this is an equivalence. It's called, again, the divergence theorem, okay? But now we have an integral over the boundary. And this is super nice because now our Newman boundary conditions are going to pop up naturally in the formulation by just applying the divergence theorem. So now I am going to apply finally the property of the transpose of a tensor. All I need to do is basically to swap these two. That is essentially the way we define the transpose of a tensor, right? So that this equality holds. So I define the transpose of a tensor, so I can simply swap these two, right? Again, I didn't need to use the property that the stress tensor is symmetric, right? I just use now the definition of the transpose of a tensor, and now look what happened. I have my W, my test function here, but then I have Cauchy's traction equation popping up, which is insane that our Newman boundary condition pops up just by applying the divergence theorem in the formulation. It's beautiful. How do you see this? Like, whoever came up with this, like, insane. I cannot grab my head around this. Okay, I'm exaggerating a bit. But you see the point, right? Now, notice that we do have a boundary that is supposed to be comprised of many parts. What are the parts? Newman, Dirichlet. Right? Those parts are mutually exclusive, so they cannot overlap. In other words, if you pick any point in the boundary, you either know the displacement or you know the traction, but you cannot know both, obviously, right? So these are mutually exclusive and or disjoint, right? And this is a statement that normally you say, well, gamma D intersection with gamma U is equal to the the null set, the empty set, right? And the boundary is defined by the union of this. This is the normal way you find it in books, in papers. So notice that now I take that integral over the entire boundary, and now I split it in two. I know these sets are disjoint, so I can express one fully acting on my Newman boundary, right? And another one here acting on my Dirichlet boundary, right? Now, obviously, I have changed the notation. The one that is acting on the Newman boundary, notice that I have my traction, and the one that is acting on the Newman boundary, I have my reaction traction, my reactive traction, right? Okay, but we don't like reaction, right? So what do? W is 0. We make this guy equal to 0 so that this goes to 0. That's what we do. Yeah? And that's exactly what we have in the next slide. So the variational form of our dynamic equilibrium equation is basically find U and consequently, eventually, U dot and U double dot, so the velocity and acceleration, so that this expression holds for all W's in some, again, conveniently chosen vector-valued function space. Yeah? So far, it's very straightforward. It's essentially the same as in 1D, and that is why I like starting with 1D, because, yeah, the extension to 3D is very, very straightforward. Yeah? And again, we discussed this already, that term on the with the reaction drops just because I choose functions or test functions that are vanishing at the Dirichlet boundary, all right? Yeah, we talked about this. Yeah, and there is a little trick that we have to, I'm going to briefly touch on this because everything so far we dealt with prescribing 0 Dirichlet boundary conditions. But what happens if you want to actually prescribe a value, right? We want to prescribe certain displacement at part of the boundary. That is a non-homogeneous essential boundary condition, right? So you want to say my displacement at this point is going to be equal to 1 meter, whatever. Right? So, okay, well, in finite element analysis, we deal with this by creating a so-called linear variety, it's called an affine space as well. Essentially, you take a space that satisfies the homogeneous boundary condition at Dirichlet boundaries, and then you translate that by a function that satisfies the Dirichlet boundary condition. Right? So essentially, if you take this guy here, it's called a linear variety. This U tilde satisfy a priori our boundary condition, and this V naught is the same space I use for the test function. Right? In other words, every single function that I take from this linear variety satisfies my Dirichlet boundary condition. So when I plug some function from that linear variety, then I get a really nice formulation because the effect of the prescribed Dirichlet boundary condition goes to the right-hand side and becomes part of the force vector. And again, I don't want to delve too much in this, but I will give you more, if you are interested in this, how this works, I'll give you the book, yeah, so that you can take a look at all of these subtleties because, yeah, they are important. If you really want to understand how this works, then you have to read a little bit more, okay? Okay, now I want to show you that everything we have done so far is actually equivalent to the so-called D'Alembert's principle, which is the dynamic principle of virtual work, right? So people coming from the dynamics field, they don't really look at, let's say, method of weighted residuals. They start probably from D'Alembert's principle, right? And so everything we have done so far is actually equivalent. How is that? Well, let's take a look at this term here. We have the gradient of W that is a, what? It's a second order tensor and it's contracted by my stress tensor, which is also a second order tensor. So let's take a look at that. Actually, for the first time here, I'm going to be using the property that the stress tensor is symmetric. Why? Because if I use the property of the symmetry of the stress tensor, this equality holds. I can say that grad W contracted with sigma is equal to the symmetric part of W contracted with sigma. And what is that? By definition, the symmetric part of that tensor is 1/2 of grad W plus grad W transpose. And look how this looks like. It looks like it's here, like our linearized strain, right? It looks pretty much like the linearized strain, but of course it's not the actual strain because it's not a function of U, it's a function of W, right? So you can think of this as some sort of virtual strain. Thank you. This is going to be our virtual strain. What happened? Something happened to the screen. Okay, we have a glitch. Yeah, virtual strain. Okay, so if I take and I call this symmetric part of grad W as delta epsilon, and this is going to be my virtual strain, and I say, well, my W is my virtual displacement, right? Obviously, it has to be kinematically admissible. I have to satisfy, let's say, if I use homogeneous boundary conditions, remember that our W has to satisfy homogeneous boundary conditions, so I have to ensure that is the case. Then I can basically plug back in the equation, and then I get this expression here that you may already recognize as D'Alembert's principle, right? So I have my internal energy right there, so stresses contracted with the virtual strain, and then I have my inertial term here, and then on the right-hand side I have the effect of the body forces and the tractions on the Newman boundary. So again, just to point out that everything we have done, starting with the method of weighted residuals to get to the variational formulation, eventually ends up being exactly the same thing as our D'Alembert's principle, okay? All right, now we move on and we discretize. So we are no longer going to be working in infinite dimensional spaces. We take finite dimensional, in fact, finite element dimensional spaces. So we discretize our mechanics potato. We're going to subdivide that. If we're in 3D, let's pick tetrahedra. So we have our tetrahedral mesh, and then of course, because of the fact that our potato was curved, and now we're going to be using linear finite elements, there is going to be some discretization error, unless of course the domain happens to be a polygonal mesh in 2D or polyhedral mesh in 3D, and so you can, let's say, exactly represent your boundaries. Unless that is the case, there is going to be some discretization error, which is okay. Again, we can live with errors. We can, if we can understand where the errors are coming from and control the error because we reduce somehow their magnitude, then we are in good shape, right? That is what it means. Okay, and we do the same thing. Now we are going to take the trial solution from a finite dimensional space, the same for the test functions. And remember, I'm picking this from the same spaces, right? And that is going to lead to the Bubnov-Galerkin approach. And I said earlier in the one-dimensional case, I said that was very nice. And it's very nice for many reasons I did not discuss. One of the reasons is that if you choose the functions from the same space, you have basically symmetry on your final matrices. Symmetry is great. Why is it good to have symmetry in your stiffness matrix, for instance? Huh?
Positive solutions.
Positive solutions?
Positive definite.
Yeah, it is positive definite or semi-positive definite if you don't apply boundary conditions. So you may still need to prescribe the solution somewhere to have positive definiteness. But symmetry is good for other reasons. Why is that?
You can use symmetric solvers.
You can use symmetric solvers, right? Like
Conjugate gradient.
Cholesky factorization, for instance, right? Meaning you can have less operations. What else is less? If the matrix symmetrics. Huh?
Computational time,
Why?
because you're solving for lesser number of.
Yeah, but what else is less?
Memory usage.
Memory usage. Why?
You don't need to store the whole.
You don't need to store the whole matrix. You just store the upper triangular matrix, right? So symmetric matrices are great. And the Bubnov-Galerkin approach leads to these problems in mechanics, to symmetric matrices. Okay, so let's move on. If I write my trial solution like this, and I write my test function like this, exactly the same thing we did in the one-dimensional case. U is going to be my global degree of freedom vector. That again, in this particular case, we can call it the displacement vector because the choice of functions, I'm going to choose functions that are nice functions, satisfy this Kronecker delta property, and they have the partition of unity property as well, right? So because of that, I can call this my global displacement vector. So now that I'm in 3D, I basically write my shape function matrix. It's no longer a vector, it's a matrix this way, right? And just to give you an example, these are two-dimensional element types for the triangle. And of course, I don't have a lot of time to get into the details of what we actually do in finite element analysis, because in finite element analysis, we normally work with the so-called isoparametric formulations, right? Isoparametric, who knows what it means? Yeah?
You use the same shape functions to define your geometry.
Yes, exactly. So the shape functions that you use to define the field are the same used to define the geometry. That is called isoparametric. Again, a particular choice that is normally taken when we deal with finite elements, but not the only one. You can have subparametric or superparametric formulations. But I don't have a lot of time to delve into those. So what I'm showing here is essentially the linear shape functions from a triangle, right? The triangle lives in this canonical element or my master coordinate space, and then that is mapped to the actual triangle in physical space through the same shape functions that are used to map the field, right? So this would be the linear shape functions for a triangle, and this would be the bilinear functions for a quadrangular element, right? Again, the quadrangular element living in some parametric space, always there because, well, we have integration rules defined on that space, right? So when we do integration, we actually do numerical quadrature of those matrices. And so all the integration rules are defined here. So there is some transformation to the physical space. So there is some Jacobian mapping involved into this. And so I don't have time to delve into this. For those of you who are in Delft, of course, you are more than welcome to come to my class. I delve deeply into all of these concepts. So if you want to learn more about these formulations and even more PFEM formulations, the P version of the finite element method, I also discuss a priori, a posteriori error estimates. So we have all these more advanced concepts of finite element analysis in my class. Or you can look at the YouTube videos. I have all my lectures there if you are interested in learning about this. Yeah.
The stiffness matrix is also sparse, right?
Yeah, that's another nice property. It's a beautiful property. Actually, the main reason of the success of the finite element method is because the matrices are sparse. Because before the finite element method, we had other methods, right? Everybody heard about the Rayleigh-Ritz method? Yeah? It's basically the same thing. It's a Galerkin approach. It's just that your functions are global, right? They are not constrained to be non-zero only in little elements or little portions of your domain. So these are still widely used, the Rayleigh-Ritz, right? Some people now in the dynamics community, they call it Galerkin, but all of these are Galerkin formulations, right? All of these are Galerkin formulations. But the idea of having the functions acting globally in your domain, again, people in the dynamics field still use this because some very simple geometries, you can use trigonometric functions to represent modes, for instance, that are global to your domain, right? Those lead to dense matrices, and dense matrices are not nice for many reasons. They require more storage, and well, sparse solvers are faster also, right? That is the other reason. So the success of the finite element method is, I would say, mainly because we are dealing with sparse systems. Yeah? Okay, so let's move on. Now we do the same thing we did in the one-dimensional case. We have this finite element E, and now we want to set up equilibrium of this little element, right? And so we have, if you notice here, I now look at virtual strain, let's say, right? Contracted with my stress. So this is the same expression. Now that I'm in a finite dimensional space, notice that I have my superscript H everywhere, right? Just denoting that I'm already at the discretized stage. It's not infinite dimensional. I am not dealing anymore with the exact solution. I cannot obtain the exact solution, right? All I'm hoping is to get a solution, and again, is good or bad, it's going to depend on many things. Your finite element mesh, you can check whether your solution is accurate by many approaches. but we accept that there is going to be an error associated with our choice of our trial solution. We accept that, right? Okay, now we are going to express, we're going to use the same strain displacement matrix. So if I write the strain times equal to the strain displacement matrix times W. Remember, these are just coefficients, and I use lowercase again because I'm at the element level. And my stress is going to be now C times B times U. C is a matrix, it's not a fourth order tensor anymore. So somehow I managed to lower the rank of my four-dimensional vector to a two-dimensional vector. And I'm going to go quickly through this, right? We use something called void notation. And so the equilibrium at the element level is written like this. And now, well, this has to hold for all vectors in Rdn, where R is the dimensionality of the problem and n is the number of nodes that you have in the element. So if you're dealing with, let's say, a two-dimensional problem that is a triangle and has 3 nodes, it's 2 dimensions, so R6, right? And so because this expression has to hold for all 6-dimensional vectors, then obviously this thing here has to be equal to that. And this is the trick that we play to get rid of those coefficient vectors W. And then this leads to our local system of dynamic equilibrium at the element level. All right, let's talk about how do we reduce the complexity of our operations so that we can fit them nicely in matrices and vectors. Well, we use something called void notation. So void notation, if you remember, the relationship between stress and strain is this one. So we have an object, a fourth dimensional tensor is an object that operates on a second order rank tensor to produce another second order rank tensor. And so since we don't like to deal with that, we basically change and we use the symmetries of our constitutive tensor to reduce the number of components that we store and also to reduce the rank of the tensor. So you can actually have this, but instead of writing it like that, we can choose sigma to be represented as a vector that you have here in 2D. The same with epsilon, we're going to represent that as a vector. And now the relationship between these two is going to be provided by some matrix C that essentially is going to produce the same result as that. That is the whole idea of void notation. And you can do that very straightforwardly. And then now I have a matrix that stores the coefficients of my fourth order tensor. I'm taking advantage of symmetries of that tensor. Now, when we do that, of course, the whole point of doing that is that this contraction remains the same. Otherwise, it makes no sense, right? So what is that contraction? Remember, that contraction pops up in the internal energy, right? So that is energy. So the energy has to be the same. So whether you choose to have the more complicated high order dimensional tensors or the void notation involving lower dimensional tensors, the objective is to have this thing being the same, right? The energy has to remain the same. Otherwise, you're either removing or introducing more energy, right? Okay, well, the C matrix, this is, for instance, the way you would write them for 2 dimensions and for 3D. Again, I'm going fast through all of this because it should be known to all of you. But this is the actual way we represent that relationship, Hooke's relationship in finite element computations. The strain displacement matrix now takes a slightly more complicated shape. When we deal with void notation, the strain displacement matrix B, remember, it's called strain displacement because it's relating the strain to the displacement the displacement vector, right? Now I have to apply this delta differential operator to each one of the shake functions, and here I write you the way it's written for 2D and 3D. And again, it is written like this so that void notation works. It's just bookkeeping, so I'm making things very simple at the moment. It's not so simple, but of course, I don't have time to delve into all these ideas at the moment, okay? Eventually, we get to a strain displacement matrix that looks like this, right? So my strain displacement matrix, if you take just the first shake function, this is for 2D, of course. So if I take this differential operator and I apply to the first shape function, you obtain that guy here. All right? And so you see you have dphi1 dx, 0, 0, dphi1 dy, and then the cross terms. dphi1 dy, dphi1 dx. So everything up to this point is the first matrix, the first shape function. Then this is your second shape function, and so on. And so this matrix is going to have dimension 3 times 2n. 2n in this case because the dimensionality is 2. This is 2D, and n is the number of degrees of freedom. So for instance, in the case of a triangular element, we have 3 nodes. How many degrees of freedom per node? 2 degrees of freedom per node times 3 nodes is 6. So this is a 3 by 6. So the integrand of our matrix, remember, it was B transpose CB. So this is a 3 by 6. So B transpose is 6 by 3. Multiplied by the constitutive vector, which in 2D is obviously has to be, it's a 6 by 3 multiplied by a 3 by 3. Multiplied by B, which is a 3 by 6. In the end, the integrand of that stiffness matrix is going to be a 6 by 6. So for the triangular element, you obtain a 6 by 6 matrix. Okay? All right. This is basically the final expression for our dynamic equilibrium equation, discretized at the element level, right? Where this component here, again, this is your local stiffness matrix, this is your local mass matrix, and this whole thing is your force vector. All right? And so we get to the final discretized system of equations by simply doing the assembly operation again. So everything so far is essentially the same as in the one-dimensional case. Again, assembly means add up the right components of your local arrays at the right locations in the global arrays. That's all it means. All right? So we're done with the final element equations. This is basically the way you obtain the discrete equations, algebraic equations that you can start solving. But we need to look into how you solve that. And that is the subject of the next and final part of the lecture on time integration. So we stop again for 10 minutes and then we continue. All right?